Hello everyone, welcome to our fourth topic. This is on nomenclature, and this is going to be our first video that we're going to watch asynchronously. Before we begin, I want to just remind you about some of the reasons why we're doing this asynchronously. Hopefully we've talked about this in class, but just as a reminder in case it hasn't sunk in, I really want to talk about our why and why we're doing this video this way. One of the biggest reasons why is so that you can kind of go at your own pace. Often when we do a group lesson, we kind of have to go at the pace of the average student in the class. And maybe that means we're going too slow, maybe that means we're going too fast. But if we design a lesson as a YouTube video that you watch at your own pace, a couple of advantages. You're able to pause the video, you're able to fast forward or rewind. There's actually going to be a couple of slides in this particular lesson where I'm going to give you kind of a work or a practice slide to test out whether or not you understand the concept. And you can pause the video, and then depending on how long it takes for you to try to solve the questions, it might take you 2 minutes, it might take you 30. But everyone can kind of go at their own pace, and then that gives you that ability to do the pause, the rewind, those sorts of things. Ideally, the goal behind this is for you to watch this video in class. And so the other advantage is if you have a question, rather than stopping the entire class, putting up your hand and saying, hey, I have a question about something. A lot of kids sometimes are a little shy and they don't want to pause the whole class. Well, now you just have to pause your own video, and then you can put up your hand and ask me, and I'll be literally, hopefully I'll be in the classroom. Be able to ask me for help. Now, obviously you can watch this video at other times too, but that's the design behind this. And so it gives a lot of flexibility. So anyways, that's our why. And I always pick lessons that I think really fit the concept, where it's the most likely lesson for students to have the greatest diversity of needs. And this is one where some students, they've already learned this because they learned it in grade 9. And for other students, this may take a while. And so this gives you the ability to go at your own pace. So with that being said, let's get started. Our goal today, nomenclature, is basically all about this word right here. We need to be able to name things in chemistry. We need a universal scheme. Okay. As an example, when you look at an object, the English language normally has just one word for it. It's a chair or a desk or a window. And sometimes there's synonyms where there's more than one word for it, like, is it a hat or a cap? I mean, maybe no one says cap anymore. My grandfather used to say that. But like for the most part, we want to have one word for one item. And in chemistry, that's really important because we need to make sure we're using the same terminology. So the most common convention we use is known as the IUPAC convention. It stands for the International Union of Pure and Applied Chemistry. And it's more or less the standard method that we use in science and chemistry for naming things. Ideally, this means that someone that's working in England, someone that's working in Russia, someone that's working in Australia, someone that's working in Brazil and Canada, they're all using the same naming scheme. Because there's nothing worse in chemistry than you're trying to talk about something and you're not on the same page, right? One person's talking about one compound, one's talking about another. So that's our goal. We need to talk basically about the right vocabulary. And I might have used this analogy before in class. If I haven't, this is the one that I like to use, is that we've already learned about elements. And elements are, in a way, like your ABCs. They're like your letters of your alphabet. And then as someone is learning a new language, once they learn the alphabet, the ABC, eventually they need to make, the chemistry analogy was they need to make compounds. And in order to be able to name a compound, that's like basically when you start putting your ABCs together and you make a word. And eventually we're going to get to the point where we're going to talk about a chemical equation. And that's kind of the culmination of this course. And an equation, the analogy for that would be like a sentence. And once you can put those words together in a sentence, you've gone from knowing your alphabet to knowing how to make a word to being able to do something with it. What we want to do today is take you from knowing your elements in the periodic table and being able to name compounds. And so that's where this flowchart comes from, is that there are many different types of compounds that we're going to need to learn how to name. And so I've got a flowchart that helps kind of explain some of the most common types. Ideally, you should have learned about this in grade 9 science. At the very bare minimum, you should have learned how to name covalent compounds and binary ionic compounds. And then just depending on who taught you and how far you decided to go, you may have learned about a couple of the, I don't know, I wouldn't say like exceptions to the rule, but like a couple of like the specialty cases. That's what these two are. Multivalent and polyatomics are specialty cases. And every one of them requires a different naming scheme. this is actually, although we are in the section on chemistry right now, this is somewhat like biology, where in biology you learn about taxonomy and how to name things like genus and species, and there's a very specific naming structure to it. And that's basically what this is you have to identify what type of compound is it, identify how it bonds, and then recognize what naming scheme to use. So that's what we're going to go through today in our lesson. Before we get there, a little bit of review just to make sure that we're all on the same page. We are now attempting to go from elements, which are like our letters, to compounds. And just a reminder of some of the vocabulary we've learned before. Elements are named and written based on their allotrope. And so when an element is by itself in its elemental form, like for example calcium, or iodide, or hydrogen, or lithium, some of these things come in groups of one, naturally on their own in elemental form. Calcium and lithium are both things that come in a group of one. But both iodide and hydrogen are things that come in groups of two, and those are known as the allotrope. Some things are diatomic, some things come in 3s or 4s or 8s or more than that. So that's one thing that elements have in common. Another thing that you need to be aware of is the isotope. Isotope. And that's where you can have, like, say, sodium-22 versus sodium-23. And the only difference between these two things is that one has an extra neutron. The final thing we hopefully have learned about so far is the idea behind ions. And ions mean that you change the number of electrons. And so this chlorine right here is a chlorine negative. It means it must have gained an extra electron. Now, those are all for when things are in their elemental form by themselves as like a single letter of the alphabet. If I use the word analogy, okay, I know that Na is really 2 letters, but this is like a letter, sodium and calcium. What we're now going to want to do is talk about compounds where we put Na together with Cl and make NaCl, or H2O, which hopefully you're familiar with, water, or CO2, carbon dioxide. We're going to learn how to name these things. So there are 2 basic broad headings. If you go back a slide here to this nomenclature idea here, there are 2 main broad headings that we're going to talk about. There's the covalent and the ionic compounds. And the big difference between them is what is it that is bonding. In the molecular or covalent, there's kind of a synonym for that. There's 2 different words that kind of mean the same thing. It's always between 2 nonmetals. And so we're looking for the things that are on the extreme right-hand side of the periodic table. And the thing about them is that they share their valence electrons. Hopefully this isn't new information because it is grade 9, but I've got some slides to remind you about how this works. The ionic compound is kind of an alternate version, and it involves the metal-nonmetal. And what's different about them is that there is a change, a transfer, if you will, of electrons. And those are the differences. Is one object shares electrons and one gives and takes them away between the anions, which are negative, and the cations, which are positive. So, hopefully you've seen this before. This is hopefully a bit of a review. If it isn't, make sure you let me know, and I'll see whether I can find you some videos from my grade 9 class, and maybe we'll try to catch up. Because that's one of the things that's important to do, is to figure out what are your blanks, what are you missing. What do we need to fill in the gap of, in case you're not familiar with this? So if you're not familiar with the idea of an ionic compound between the metal and the nonmetal, the idea here is that sodium as an atom, sodium is atomic number 11, so it would have 11 protons. And as an atom, it would have 11 electrons. And chlorine would be atomic number 17, so it would have 17 electrons. But those are not what they would like to do, because this sodium right here has 1 valence electron in its most outermost ring. And that's not overly stable. It wants to have 8. It wants to fit the octet rule. And so really, this guy would like to lose an electron. So hypothetically, let's say this guy loses an electron and he drops down from 10 protons to, and 10 electrons down to 10 protons. Sorry, rather than it being 11 protons, 11 electrons, let's make it 11 and 10. Well, now this sodium becomes a positively charged ion because it's lost an electron. Well, chlorine is a natural person who might want to take that electron, because chlorine has 1, 2, 3, 4, 5, 6, 7. It's 7 out of 8 for its valence electrons. There's kind of like an opening right here, where if this electron could kind of move into this opening right here, then that would basically make both of these elements happy, because rather than this guy being 17 protons, 17 electrons, it would now be 17 and 18. and it would now have a negative charge. And you're probably familiar with the opposites attract kind of concept. If this thing is positively charged and this thing is negatively charged, they are going to want to become attracted to each other, and it forms a bond. This is known as the ionic bond. So here's kind of a picture of what I ended up drawing on that last slide there. Sodium becomes positive, chlorine becomes negative. The electron is transferred from one location to the other, and the ionic bond gets formed. So let's review how to name these. Again, if this is something that you're not familiar with and you're like, ooh, I don't really remember this from last year, pause, ask for some questions, ask me to help, ask me to go over it again, right? But if this is review, this is a fairly straightforward naming scheme. Here's how you name it. We always name the cation first. Remember, cations are positive. The acronym CATS have pause. CATS have pause. Cations are positive. Is a way of remembering that. So cations always go first, and then ions always go next, and we always change the ending to IDE. That's it. So like, for example, in AgCl, Ag is +1, Cl is -1, and they're just going to kind of naturally fit together. +1 and -1, they'll fit, so you have a 1-to-1 ratio, and you call it silver chloride. That's it. Perfect. In another example here, you have potassium and oxygen. Well, if you look up potassium's most common charge, it's +1. But if you look up oxygen's most common charge, it's actually -2. And that kind of explains why there's a little 2 down here in the corner. Now, I'm going to draw out what I do for my manipulatives. Maybe you've seen me use these before, but potassiums, I have some little manipulatives that look kind of like this, where this would be like a +1. And this right here would be like another +1. Whereas I might have my manipulative that looks like this, where this is kind of my -2, the way it kind of looks like this. And so this is a -2 charge right here. Because what happens is this +1 can kind of fit into that location. This one fits into that location. And ultimately, the 2 of these bring a net of +2. This has a net of -2. Now they are equal to each other. That's a really important thing about ionic compounds, is that there needs to be an equal and opposite. If this is +2, that has to be -2. And so now that that's the case, well, that means you need to have 2 of the potassium. So there's a little 2 that goes down in the corner, letting us know there's 2 potassiums there. And so the way we name it is potassium, and then oxygen just becomes oxide. Finally, let's do one more here. I'm going to draw this out a little bit better here. I'm going to draw it with maybe a different method. Maybe I've shown you my little sticky manipulatives already. But maybe you like drawing it like this. Aluminum is a +3 charge, and sulfur is a -2 charge. And so the way that you have to kind of put it together is this would be 3 positives, and then the sulfur has 2 negatives. And as it is currently, it's a 3 to 2. That doesn't balance. That means there's an extra positive. So you might say, well, what if we use 2 sulfurs? Well, now it's 4 to 3. That doesn't work. What if I use an extra one? So now we have 2 aluminums and 2 sulfurs. Well, that's still not going to work. Well, let's use 1 more sulfur. You know, the word we're looking for here is lowest common multiple, because we actually have a total of 6 positive on this side now and 6 negative on this side. And so we now build a neutral molecule, a compound that is effectively neutral. And what we did it is by having 2 of these aluminums and 3 of these sulfurs. And so the name for it becomes aluminum sulfide. So hopefully that's a little bit of review. If it's not, like I said, pause the video, ask me for some help on it. So I've got some examples here. Let's try these together as a group just to kind of practice. And then I've got a slide in a little while for you guys to kind of do some practice on. So let's do sodium chloride. Sodium is Na, and it has a charge of +1. Chlorine is Cl. It has a charge of -1. And those just fit perfectly together. +1, -1, awesome, 1-to-1 ratio. I should remind you that standard convention would be to remove the charges after you're done. Don't leave them kind of sitting there. If you ever write Na+, that kind of means that it's the ion by itself, but this sodium and chlorine are actually bonding together, so we like to write it maybe right next to each other, NaCl. Let's try another one. Aluminum chloride. Aluminum is Al, and chlorine is Cl. Now, aluminum is a +3 charge, and chlorine is -1 charge. And if you kind of consider how that might look, I have the manipulatives that I use here. So this could be how I draw my +3. There's 1, 2, 3. So there's pluses on all those. Well, it means you're going to need to have a negative to go here, a negative to go here, and a negative to go here. And so how many individual negatives will you need? Well, you'll need 3 of them because they each come at -1. So you'll need 1 at +3 and 3 at -1. So when you're done kind of like seeing how all that fits together, hopefully you'll recognize that the formula will need to be AlCl3. For the final one, calcium is Ca and nitrogen is N. And in terms of their charges, calcium is +2 and nitrogen is -3. Now you can kind of draw this out if you'd like, but honestly the best concept is to understand lowest common multiples. What do 2 and 3? What's the lowest number that they both have in common? 6. If I do a couple of +2s and an extra -3, all of these will add up to +6. Both of these will add up to -6. That's perfect. So how many calciums did you use? That little 3 that we put down here says there's 3 calciums you need for every 2 nitrogens. And so this is the appropriate chemical formula for calcium nitrate. Now that's one of the more challenging things to do is write it in that direction, because the other one's actually a lot easier. If I just give you a formula and I ask you to name it, it's fairly straightforward. You just literally name the first thing you see, name the second thing you see, and then just add "ide" at the end. So K is potassium, and Br is bromine, but we change it to bromide. So potassium bromide. Be is beryllium, and oxygen just becomes oxide. Sr is strontium. So F, well, F is fluorine. Fluorine becomes fluoride. Cool. Now this is actually, I'm going a little bit faster than I probably would go in a normal class. I just want to point out that the reason I can go faster is for some students, you're like, yep, got it, learned it in grade 9. Chris, move on, let's go a little faster, right? For some of you, you may be going, ooh, no, don't go too fast. Well, now you have the ability to rewind, pause, slow down. And so don't just write down the answers. That doesn't just help you learn, right? Really make sure that you understand the concepts. So if you don't, ask me to come over and take a look, see whether I can try to help explain it better. Okay. Now, the other thing you should have learned from grade 9 is how to name a molecular compound. And molecular compounds are a little bit different. Those, again, were the ones that were between 2 nonmetals. And so there's a different naming scheme. What you end up doing is you always have prefixes. And the prefixes are based on a chart, which I have right here. Here's the chart. If you ever have 1 of something, you call it mono. If you ever have 2 of something, you call it di, like carbon dioxide. 3 is a tri, 4 is tetra. So you end up using these prefixes, and then you name it according to your first and second elements, and you change the ending to "ide." Okay. So here's just some basic notes on these ones here. Molecular covalent bonds are formed when nonmetals bond together. Remember, nonmetals are the ones that if you have like a periodic table, say here's a periodic table, here's a real rough one here. Looks kind of like this, right? All those ones down there. And there's that staircase line. The nonmetals are the ones that are over on this side over here. Pardon me. And they're always the ones that have negative charges. And so the big thing about these is that they share their electrons. So here's that slide again that has all the prefixes. If I could give a suggestion, feel free to write this down somewhere in your formula sheet data book, whatever it is that I gave you for a periodic table. Write these down somewhere just in case you forget. Let's try some examples. Again, this is ideally some review, but if not, let's kind of work our way back in. If I look at this, I see carbon and oxygen. The first thing you'd hopefully do is recognize, oh, they're both nonmetals. I need the molecular naming scheme. So we would say, well, we need carbons. We need oxygen, but oxygen will change to "ide." And then the last thing we need to do is write out the prefixes for each of these things. Now, there's a bit of a rule that says that if you ever have 1 of something and it's the first thing in the list, we don't write mono. So carbon we need 1 of, and so technically we need a monocarbon. But we never start a word with mono. It's just one of the weird rules of chemistry. We just try to save time if we don't ever start with mono. So But we do have 2 oxygens, and 2 is the prefix di. So that's where carbon dioxide comes from, which hopefully you're familiar with. It's a fairly common compound. Now you'll notice that there's actually the exact same 2 elements being formed again here, but this time the ratio is different. Rather than a 1:2 ratio, there's a 1:1 ratio, which means that there's 1 carbon, which we don't actually put mono in front of it, but we do put mono in front of the oxygen to let you know there's only 1 oxygen. So carbon dioxide has 2 oxygens, and carbon monoxide has 1. Basically the naming scheme. For this next one here, we would say nitrogen, because I see N, so that's nitrogen. And then hydrogen would change to the word hydride. Remember, it changes to ides. And then the last thing is we need to put prefixes in front. So this time it's not 1 for our first one. Nitrogen has 3 in front, so 3 becomes a tri, like tricycle. And then 6 is hexa. So it becomes a trinitrogen hexahydride. So those ones are not so bad. Writing the formulas the other way is actually really easy. All you got to do is just read how many the prefixes are. It says you have silicon. All right, that's Si. There's no thing in front of it, so there must only be 1. Then there's fluoride, that's fluorine, so I must need some fluorines. And the tetra means I need 4 of them. Here I see the word phosphorus. Phosphorus is P. I see oxide, that's oxygen. I must need O, so I need P and O. The question is how many of each? Well, the tetra in front of phosphorus means you need 4. And the deca in front of oxygen means you need 10. So this is P4O10. Again, if I'm going too quickly, make sure you pause as you need to, because I will go quicker during these videos. Last one, nitrogen, dinitrogen monoxide. Okay, well, maybe you go a little bit quicker. You see nitrogen first, then you go back and see the di, so we need 2. And then monoxide, okay, so the mon means you need 1 of something. 1 of what? Oxygen. Okay, 1 oxygen. Now, you could put a 1 there, but standard convention in chemistry is we don't usually write a 1 anywhere. So there's dinitrogen monoxide. Perfect. Okay, now here's one more thing we need to do before we do a practice slide. There are some common chemicals that involve hydrogen that have just been given like a formal name. And this still counts under the IUPAC naming system, actually. Unfortunately, there are more than 1 name for some chemicals. It's quite frustrating. As an example, this first one on the list here, you know as water, H2O. But technically it should be actually known as dihydrogen, because you have 2 hydrogen. And then you have 1 oxygen, so it should be known as monoxide. Maybe you've heard that before. That's actually one of the other names for water. But a lot of things are given a formal name that we use as well. So often you need to memorize these ones. And so these are 5 that I'd like you to know. Water, methane and ethane, methanol and ammonia. And I recommend write them down somewhere on your formula sheet so that if you come across one of these ones right here, if I ever talk about ethane on an assignment, you're like, oh yeah, okay. One of those common ones, it's a C2H6. Okay, so let's do some practice. Here's what I'm going to do. I'm going to pause the video, and I want you to pause the video as well, and I want you to try some of these and see whether you can do this. This is, like I said, ideally these are outcomes that are really from the grade 9 curriculum. Maybe it's been a year and a half since you've done this. I don't know. Maybe it's only been a few months. But spend some time practicing. You can't just watch the video and go, oh yeah, I know, I've got it. Try it, see whether you get it. And if you're struggling, call me over, ask me for some help. What I'm going to do is I'm going to pause the video now, and when I unpause the video, I'm going to have all of the answers on the slide. So this is your fair warning. Pause the video now, and when I start up again, it'll have all the answers. Okay, so we're back, and we should have all the answers written out here. I'm just going to put a little star next to the ones that involved the molecular naming scheme, the ones that involve needing to have a di and a tri. This one here and this one here, those needed dis and tris. And then you'll notice that these ones over here, some of them had dis and tris. That would be these ones right here, including the last one, water, the dinitrogen monoxide we talked about earlier. So hopefully you've tried this yourself. If you have any questions, please let me know in class. Sorry that maybe my writing's not great to be able to read. There's not a lot of room in here, but hopefully you can read what I've got there. And yeah, we're going to move on. So let's move on just to a quick review then visually of what happens differently between these bonds. Again, in the ionic bond, you've got someone with a spare electron, an extra electron, and it literally gives one away. It transfers the electron so that this guy right here becomes positively charged because he loses an electron, right? And this guy right here becomes negatively charged because it gains an electron. So this is like Na positive and Cl minus, and they bond. Whereas in a covalent bond, they're going to share their electrons. They're going to collectively pool their resources so that everybody has access to 8 electrons. These guys right here have 8 electrons in their ring. These guys right here have 8 electrons in their ring. One of the analogies I use for this is imagine you need to go buy something, and for sake of argument, let's suggest that it's $8. And so this guy right here, he has $1. And this guy over here, he has $7. And if you haven't figured this out in this analogy, the money is your valence electrons. So does this guy have 8? Well, no, he's at 1 out of 8. Does this guy have 8? Well, no, he's 7 out of 8. So what this guy here does is recognize, oh, look, I don't have enough, right? So maybe what I can do is rather than me right here making it so that, like, I, can't get there, maybe I'll just give my dollar away here, right? And so what ends up happening is I give my dollar away. This guy now has 8 out of 8. So this guy goes down to 0 out of 8. He literally gives this guy his dollar. And what ends up happening now is, yay, we're good. Now we have 8 out of 8 over here, and there's enough so that everybody's happy. Right? What happens in this scenario right here is a little bit different. It's almost like what you need to consider is that this guy right here was like, say, 1, 2, 3, 4, 5, 6, 7. Let's pretend that this electron right here was really supposed to be with this guy right here. So this guy was 7 out of 8. And this guy over here, let me even color code those just so that maybe you can see that. So let's say that before they were bonded, all these red ones were attached to the left-hand side guy. But then we'll go with purple. Then this guy over here had all of these ones and had this one. And so this guy right here was also 7 out of 8. They're both super close. Now you might think, Chris, the math on this really doesn't work. And that's where my buying something like for $8 analogy doesn't kind of breaks down, because that's not how this works. What you just need to do is have access to 8 electrons. So what ends up happening is this guy right here keeps 1, 2, 3, 4, 5, 6 entirely for himself, makes the 7th one be a shared one. It's part of like the communal pool. And so number 7 is sitting right here, but they both get access to it. Well, this guy over here also has 1, 2, 3, 4, 5, 6 just for itself, but the 7th one kind of goes in the shared pool, which means that really for red, well, this one right here is red's number 8. And for purple, this red one right here is its number 8. And so now they both have access to 8 electrons, but they had to share their way to get there. And it's a bit of a different way because, it doesn't really work in the buying something analogy, but hopefully you can visualize kind of the differences between those bonds. So here's another picture that you can kind of use to help illustrate how these two things work. Let's move on here. So let's talk about one of the unique sort of special cases. And you may or may not be familiar with this. This may be something that your grade 9 teacher taught you. This may be brand new to you. If you look carefully on your periodic table, specifically in the transition metals. If you're not familiar with the transition metals, imagine you have a periodic table that looks something like this, where there's the periodic table looks something like that, right? Hydrogen's up there. The staircase line is over here. Those are the lanthanides and actinides down here. The transition metals are all the ones that are right kind of in the middle of the table here. You've got your iron, your copper, your chromium, all those ones there. And what's special about some of these is that there's more than one charge for some of them. And that's a really confusing thing to explain. I'm not even sure I fully understand it myself. I learned why when I was in like 3rd year chemistry in university. And it takes like, you gotta build a lot of building blocks to get there. It's not like it's a simple, well, here's the reason why. We gotta explain how orbitals work and how orbitals get filled and how transition states are which ones are stable and which ones are not. So I don't think I can give you an adequate explanation as to why some of these things have more than one charge. I just need you to accept that there are some atoms, there are some elements that have more than one charge. And so as a good example, I'd like you to take a second and try to find chromium on your periodic table. Look for chromium. If it takes a second here, pause the video. Okay, so hopefully you found chromium. And one of the things you'll notice is that chromium has hopefully 2 charges listed at least. There's hopefully a +2 and a +3. And chromium also, I believe, has a +6 charge. If you find a very detailed periodic table, it might list many different charges. There are some elements that have many. For example, tungsten, which is letter W for some reason, is +2, +3, +5, +6, and +7 if you have a periodic table that lists all of the possible charges. We call them valence states. That's kind of the more official name. Copper, for example, is both +1 and +2. So now that you've hopefully seen that there are some elements that have more than one charge, a couple of thoughts. First one is, whichever one is listed first is the most common. Okay? That's why they're listed the way they are on your table. There are some tables that just list all of them. It doesn't tell you which one's most common. You'd have to research that some other way. So here's why this is important. Let's say that we wrote out 2 different compounds here. One is Cr2s3 and one is CrS. I'll write them down here. Cr2s3 and the other one is just CrS. Well, these are both chromium sulfide. Right? Both of these are chromium sulfide, but they are very different compounds, sometimes with very, very different properties. Sometimes this compound right here could be perfectly safe, and this one right here could be toxic, poisonous, cancer-causing. And they are both technically chromium sulfide. And so what we do is we have a special naming scheme, and maybe you've seen this before. Right here, if we kind of work backwards, we recognize that sulfur has a -2 charge. That's always sulfur's charge. Well, since chromium could be 2, 3, or technically 6, using some backwards logic, we might recognize, well, this one right here better be +2, because that's the only way that a 1-to-1 ratio will fit, is if you have 1 -2 and 1 +2, then that'll work, which means we're going to call this chromium sulfate. So it's still going to be chromium sulfate, or sorry, not sulfate, sulfide. Sulfide. But what we do is in the middle of the word, we put Roman numeral 2. And that Roman numeral refers to which variety of chromium we're using. And so since we're using the 2+ variety, it's chromium 2 sulfide. Whereas in this other example here, the top one, it's still chromium. It's still sulfide. However, we need a Roman numeral that's not number 2 because this is clearly a different compound. And when you work backwards, you recognize that 2 by 3 gives you 6. So right here, this better be 2 by 3, also giving you 6. The only logical possibility for this chromium was the 3+ version. So Roman numeral 3 would go here. And so you can actually have all of these different possible charges, and they give different compounds. The other thing that we'd like to work on here is something called a polyatomic. We're going to do a practice slide in a little while for you to give this some try. Practice some questions in class, just like we did a few minutes ago. Before I get to that, I want to explain the other possibility. These are known as polyatomics, and often polyatomics are listed in a chart somewhere. If you have a periodic table, again, here's your rough periodic table, looks something like that, right? Sometimes in this open section in the middle here, there's often a chart right there. And that chart lists polyatomics. And again, polyatomics are kind of hard to explain to someone who's learned 4 lessons of 10th grade chemistry. The basic concept of it is that the whole thing comes together as a group. Sometimes I like to use Legos as analogies for chemistry, right? Like you've got your red blocks, your blue blocks. Sometimes they're 4x1s, they're 1x6s. They're the ones that are thick, they're thin. Okay. Well, polyatomics are like a specialty piece where technically it's made of 4 different little things. There's like one here, 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 and here. And in theory, you could break it apart, but like it's coming together as a clump for some reason. This is like a wheel for a car or one of those, I don't know, think of some sort of specialty piece where technically it's made of 4 different little pieces, but like you really don't want to take it apart. It's not meant to come apart. It's meant to stay together. But technically there are parts to it that are smaller. But if we can accept that these things come together as a single unit, and so NH4 is always sticking together as a positive charge, NH4 plus really functions the exact same way that Na plus would do, that H plus would, that Li plus would. And similarly, OH minus functions similarly to Cl minus and F minus and I minus. All of these things right here have a collective negative charge. So they kind of bond ionically still, but you've got this whole grouping together. So I got a couple examples on here to talk about how this works. The way these ones work is that you actually have to not ever change the suffix. Okay, you never change that. Okay, so they have their own names. We never change the end to them, so you really just like name them as you see them. If you see MgSO4, the first thing you're going to want to do is look at your chart and figure out, well, which is the polyatomic. And hopefully you'll find that SO4 is on your sheet as SO4 2 negative, and it's called a sulfate. So therefore, we call this thing a magnesium sulfate. And we don't change anything at all. Most of the polyatomics will end in either ATE, an 8, or an ite. Those are typical endings for polyatomics. IDE is usually when you just have a single thing left over. Like, for example, if you have CaS, that's calcium sulfide. But if you have CaSO4, it's now calcium sulfate. So a little, slight little difference makes a huge difference. This is calcium sulfide. This one is calcium sulfate. So I got some more examples here. Here's Ba with CO3. CO3, if you look on your table, is called a carbonate. So you just call it barium carbonate. You'll notice if you look at the charges, there's +2 and -2. They just fit perfectly. Now, what if they don't fit perfectly? For example, NH4 is a single positive, but PO4 is a 3 negative. Well, it means that this entire unit, you're going to need 3 of them. So you're going to need a +1, a +1, a +1 to fit up with that -3 that's sitting there for the phosphate. By the way, NH4 is the only positive polyatomic we really ever work with. Almost every polyatomic that you're going to otherwise see is usually negatively charged. So here's the reason I point that out, though. We have to then put the entire thing in brackets. We're going to put the entire NH4 in brackets because we need 3 of all of them. If you could kind of look at this at a Lego level, it would look kind of like this. You'd have an NH4, you'd have another NH4, you'd have another NH4, and you'd have a single PO4. This guy right here is a +1 charge. This guy right here is another +1 charge. This guy right here is a third +1 charge. But this PO4 that's over here, it has a collective -3 charge, and hey, look, they all kind of balance out, and they're now technically neutral together. So the key, though, is that if you need to have 3 of them, the entire NH4 needs to go in brackets. Otherwise, what you'd have is this, NH4, 3 times, and you'd have a PO4. But this is why this would be confusing. This would actually imply that you have 1 nitrogen and 43 hydrogens. That doesn't really fit. So the 3 right here kind of is like a multiplier. It implies that everything in brackets there's 3 of, so that's why there's 3 of them there. So the name for this one, then you just name it as you see it. NH4, if you look it up on your chart, is called ammonium. And PO4, if you look it up on your chart, is called phosphate. So call it ammonium phosphate. So I'll do a couple of examples together, and then I've got an entire slide where I'm going to do the same thing. I'm going to pause. I'm going to have you give it a try for a little while. So let's look at this first one. You've got NaClO4. The reason I recognize that is because there's more than 2 things. 2 elements, but there's 3 here. There's Na, Cl, NO. So I need to go look up what the heck a ClO4 is. So this would be another good time. This is why I'm doing this video this way. If you need to, pause the video and try to find on that table of ions what the heck a ClO4 is. So hopefully you found it. ClO4 is called a perchlorate. So the way we name this is Na is named sodium. ClO4 is called perchlorate. And that's it. We don't change anything. Just name it as you see it. Try the next one, SrSO4. So again, you got to figure out who the polyatomic is. SO4 is the polyatomic. We've actually come across that earlier on a previous slide. It's called a sulfate. And you can actually write sulfur with either an F or a PH. I'm going to go with F today, so I'm going to call it a sulfate. Sr is strontium. And that's it, strontium sulfate. And it kind of makes sense the way it works because strontium is a +2 charge and sulfate's a -2 charge. So there's a nice 1-to-1 ratio for both. So we're kind of good. This one right here, you'll notice there's a bracket around it, which means that the entire NO3 there are 2 of. So let's go look up what the heck an NO3 is. So pause if you need to. NO3 is nitrate. So pause to look for that if you need to. And then Ca is calcium. And if you kind of recognize their charges, calcium is +2. Nitrate, if you look it up, is -1, but that explains why you need 2 of them, because we're going to need this entire thing twice, because if you can times that by 2, then it'll work out balance-wise. So now here's one of the exceptions you need to know. Sometimes things start with NH4, and NH4 is the thing known as ammonium. And then it ends with chlorine. Well, we don't ever end in chlorine with an N. We always change it if it's not one of the polyatomics that gets left alone. We always change things to ide, so it's going to be chloride. The suffix back to ide, but we don't ever change the ammonium. It just stays the way it is. Now this last one in this set here is an interesting one. You might recognize, okay, there's a CO3 sitting there. So if you pause and take a look and try to figure out what the heck a CO3 is, you may discover that it's known as a carbonate, which I think we had one on the last slide. And if you look at the one that comes before it, it's chromium. So you might think, good, we're done. Chromium, carbonate, bada bing, bada boom, finished, we're done. But actually that's incorrect. And the reason why is that chromium, if you remember from earlier, just a few slides back, chromium has +2, or it can be +3 are the more common ones. So we're going to have to figure out which one it is. So if you look at your periodic table, carbonate is -2. So what seems to fit? Let's just erase the work that I've got right there. What would fit best? Well, if carbonate's a -2, it looks like we have these things in a nice 1-to-1 ratio, right? We have 1 carbonate. And the reason I know that is because it's not in brackets with like a 2 or a 4 afterwards, right? There's 1 carbonate there. So therefore, if you have 1 carbonate to 1 chromium, the only way to get a 1-to-1 ratio is if chromium 2 went with carbonate 2. So we should really put a Roman numeral 2 in there and say it's chromium 2 carbonate. Again, if you have questions, if that went way too fast, right? When I make these YouTube videos, I'm going to plow through things because maybe you don't need me to spend 10 minutes on this, but maybe you need more, right? That's the beauty, is that you get to go at your own pace. So if that was too fast, slow it down, rewind, ask questions. If this is just the right speed for you, perfect, let's move on. So let's try the other half here. Let's try making a compound, calcium carbonate. The way that I would start is by writing out calcium, Ca, and then carbonate. As soon as I see an ATE at the end, you're going to need to recognize, carbonate, that's a polyatomic. Go look it up. But now we need to balance it. Is it a 1-to-1 ratio, a 1-to-2 ratio? Like what's the relationship between these things here? Remember, those little subscripts tell you how many of them there are. According to your periodic table, and carbonate is -2, which means we have a 1-to-1 ratio. But like we would never write the ones in there because first of all, it looks like we now have 31 of something, so that doesn't really make sense. We always skip writing in ones. But if we did need more than 1 carbonate, we'd put a bracket around it. But since we don't, let's get rid of that. Let's make sure that looks like a 3. So calcium carbonate is CaCO3. Try the next one, beryllium hydroxide. Beryllium from your periodic table is Be. And hydroxide, you'll learn this as you get more familiar with it, but hydroxide is one of the polyatomics. It is OH. But we're not done. We got to figure out, well, like, do these things fit? What's the ratio that needs to be between them? And so beryllium, if you look it up, is a +2 charge, and hydroxide's a -1 charge, which means they're not fitting together properly. So we need a 1-to-2 ratio, because we're going to need one of these and two of these. But I can't write it like that, because that makes it look like I just need two hydrogens. The OH comes as a functioning group together. So first of all, we'd never write that 1. And second of all, the entire OH would get a bracket around the OH bracket 2. So what that would kind of mean is that there's a beryllium, that's a +2 charge. There's a hydroxide, that's a -1 charge. And then there's a second hydroxide, that's a -1 charge. And so equal them all out, it comes out to a net charge of 0, which is what all compounds should do. Iron 3 nitrate. So the way iron 3 nitrate would work is I'd write out iron. Now, I don't actually write 3 here. That's not what it means. The 3 tells us what version of the iron it is. So I know that the iron is actually the +3 version of iron. Nitrate is NO3 if you go look it up on that table. And if you are checking, nitrate has the -1 charge to it, which means that these things, they don't fit perfectly. Hopefully, maybe I will. I have a little manipulative where there's like a couple of these like protrusions here. And so this would be a +3 guy right here, 1, 2, 3 like that. And if I bring out a single, well, that doesn't fit everybody in. So what if I bring a second -1? Well, we're still not quite there. If I bring in a third one of these -1s, there we go. Now everything fits perfectly. So it means you need one of these and 3 of these. So we have a 1-to-3 ratio, which means we need a 1-to-3 ratio, which means I need 3 of these. But again, that makes it look like we have 33 oxygens. We need to put this whole thing in brackets so that this 3 applies to everything there. Fe bracket NO3 close bracket 3. Okay, so hopefully this makes sense. Maybe you've seen this a little bit, maybe not, but we need practice. You can't just look at me do 5 examples and go, yeah, I got it, Chris, we're good. So here's what we're going to do. I'm going to throw a whole bunch of examples on the board, and I want you to spend some time trying these. Now, depends on where you are in class. This may be a kind of YouTube video that you may need to finish on your own time a bit later. My run time right now is 47 minutes, but I've still got a few more things I need to show you. So here's what I want you to do. I want you to try these examples here. I'm going to write out the answers like I did last time around. I'll do my best to try to make it neat and organized, but we're going to move on to the next little section because we got one more thing we've got to cover. So, but give this a try. Maybe you don't do it right now. Maybe you do it later at home. But don't just leave this and go, yeah, I watched it once. You need some reps. So do some practice. So I'm going to pause the video right now, and if you'd like to, then give this a try. Okay, so I'm back. I've written out all the answers. I typed out the first one, so hopefully it's a little bit easier to read, and I've written out some of the bottom ones. I'm not going to spend time in the video going over this because that's kind of the point, right? This is meant to be a time saver for some people and the chance for you to take more time if you need, because you can hopefully see this is the exact kind of lesson where some students their heads will be spinning and other kids maybe not. And so since there will be a wide variety of learners, the goal here is to give you all the flexibility you need to be able to learn at your best. I want to point this one out right here. I wrote out the answer. It's KNO2. It involved a nitrate. And you may not have actually had nitrite as one of the things that you're familiar with, because it's not nitride, I-D-E, it's ite, I-T-E. And so this is the last thing we need to explain. It's something called the polyatomic family. And that's where my last bit's going to go. Sometimes there are these polyatomics that are basically the exact same as each other, but like they differ by just one little thing. They differ by a single oxygen. Now, I have a typo in my notes here that I've just never seemed to fix. I've written that all of these things right here have a 2 negative charge, but if you actually look it up in your periodic table, they all just have a 1 negative charge, so I apologize for that part, but the rest still kind of goes the same. Here's how these families work. They're all the same as each other. Look at all of these things that I have written here as examples. There's chlorate, it's ClO3. There's chlorite, ClO2. There's hypochlorite, ClO. And there's perchlorate, ClO4. All of them involve chlorine and oxygen. It's a ClOX. And X means X could either be 1, 2, 3, or 4. And so because it could be ClO, ClO2, ClO3, ClO4, since there's kind of all of these things that are almost the exact same as each other, we call them a family of polyatomics, and they're so close to each other. And so they kind of have a similar naming scheme. And the way it works is that 8 is the reference point. Anything that ends in the name 8 is kind of where we base things on. So here's how it works. Let's say that chlorate has 3 oxygens. So oxygen 3 is our reference point. Let's say that I go down to O2. So ClO2. The way that works then is that we call that chlorite. So chlorate is ClO3. Chlorite is ClO2. Well, let's say we go down to O with 1. Well, we can actually drop 2 oxygens off of something. And so this now becomes hypochlorite. It's got the same ite ending to it, but now we add a prefix and a suffix. The chlor involves the chlorine, right? All of these involved a chlorine. The hypo means you've actually dropped off 2 oxygens compared to normal. So chlorate, base reference point. Drop an oxygen off of it so that it goes from 3 down to 2, and now it becomes chlorite. Drop an extra oxygen off so that it's down to O1, and we don't really ever write the 1, so I'll skip that, but drop it down so that it's down to oxygen, and that becomes hypochlorite. And then here's the last one. What if we go up 1? So remember how the base was O3? Let's say that you go up and make it O4. Well, that's a per as a prefix and 8 as a suffix. So it actually becomes perchlorate. And so we can actually name a whole bunch of different polyatomics just based on whether you know kind of a reference point. So if I go back to this one right here, maybe you haven't heard of a nitrite. Maybe it's not on your table. Maybe it is, maybe it's not. But maybe you've heard of nitrate. If nitrate is NO3, then logic would dictate that nitrite is NO2. And hyponitrite is NO, and pernitrate would be NO4. And so all of these things are kind of part of a family. Now, maybe they're not all listed, but you could maybe figure it out. Now, here's what some kids start to get in the habit of. They start to think, well, that means that hypo is 1, ite is 2, 8 is 3, and pernitrate is 4. And although that would be great, you'd think that that would be the logical way of doing things. Unfortunately, that's not true. If I were to give you an example, if you look one up, for example, here's one. There's nitrate, and that's NO3. You're like, okay, the 8 is 3. Perfect. Okay. But check this one out. There's phosphate, and that's PO4. So phosphate is PO4, which means that phosphite would actually drop down to PO3, and then hypophosphite would be PO2. So it's not a hard and fast rule that 3 is always the 8, but many of them do fit that way. All right, last thing. The reason why this matters is that we actually have special names, furthermore, for acids and bases. And again, you should have a little bit of familiarity with acids and bases because you should have learned about them in science in grade 10. The definition of an acid is anything that when it reacts, it releases hydrogens. And so there are many compounds that actually begin with hydrogen as the first part of the compound. And so if you have, say, HCl, that's actually an acid. If you have, say, HI or HNO3 or H2SO4, you ever see something start with the letter H? It's usually a good indicator that it's an acid. And the reason why is that it has the ability to release a hydrogen. And we'll talk about that more later once we get to chemical reactions. We haven't learned about chemical reactions because we're still learning to name things. But doing this kind of somewhat out of order as a basic rule, like I said, if it starts with H, it's probably an acid because it has the ability to release hydrogen, and that's what makes something an acid. So here's some properties of acids. Maybe you've heard these before. Acids are soluble in water, which means they dissolve. They often conduct electricity. They cause litmus to turn red or stay red, and they taste sour. Like, for example, a common acid would be like citric acid, which you'll find in, like, say, orange juice. So we have a special set of rules for naming acids, because that's what we're doing today. We're learning how to name stuff. So I'll show you that last, and then we'll call this a lesson. The other thing we got to do, though, is talk about the opposite of an acid, which is a base. And so the opposite of an acid being a base, bases are things that dissolve, but they release the hydroxide ion, which now we can talk about because hydroxide is one of those polyatomics. It's the OH minus. By the way, an acid is anything that makes H plus. A base is anything that makes OH minus. If you were to take an H plus and combine it with an OH minus, and combine the hydrogens, you'd actually have 2 hydrogens and 1 water. Well, 2 oxygens and 1. I got ahead of myself. You have 2 hydrogens and 1 oxygen making water, which is actually why acids and bases neutralize to make water. So, anyways, bases, here's some properties maybe you're familiar with. They're usually bitter. They usually dissolve. They still conduct. But bases turn things blue. But there's no special naming rules for bases. Because, well, that's actually what we're going to get to in another slide. Before I get to the naming rules, though, just let's talk a little bit of a review. Hopefully you're familiar with acid-base concept previously. It's the pH that lets you know whether something's an acid or a base. A pH of 7 is neutral. Anything bigger than 7, like 8, 9, 10, 11, 12, is a base. Anything lower than 7 is an acid. So acids are 1 to 7, and bases are, like, say, 7 to 14. And hopefully you've seen this before. We're going to do a lab that actually helps us work with acids and bases a bit. So I'm not going to spend a lot of time on that in our notes right now, because this is just more of a basic background information. The thing I really need to teach you is how to name acids. And so that's my last slide. Well, one of my last knowledge slides. We got some examples, and then we'll call it a day. So let's say you want to name some acids using the IUPAC names. There are 5 categories as well to learn. Holy smokes, we got so many rules to learn today. But don't worry, we're going to practice this a lot. Okay. So here are the naming rules. There's the possibility of it being a binary acid, where there's just 2 parts to it. And then there's your polyatomics. Remember how there's those family of polyatomics? There's the ates, the ites, the hypoites, and the perates. These families, each of them has a way of naming something. So let's look at some examples here. Let's say that you have HCl. It's binary. And the reason it's binary is because there's only 2 parts to it, H and Cl. Well, you would normally name it hydrogen chloride because you'd name it first as hydrogen, name the chloride second. So here's the special naming rule then. We call this hydrochloric acid. The way it works basically is that we start it with the word hydro because of the hydrogen. And then the "ide" makes it hydrochloric acid. That's kind of how it changes. So if you had HBr, you would call it hydrobromic acid. HF would be hydrofluoric acid. So that's one possibility. Let's say, though, that you have an acid that isn't binary. It doesn't have H with a single item afterwards. Let's say it's got that polyatomic of NO3. Well, we've learned NO3 now to be nitrate. So the way this works is that anything that ends in an 8 becomes ic, which is really what we did before because ides became ics, didn't they? Didn't anything ending in ide become an ic? But there's a hydro in front of this word. So this is hydrobromic and this is hydrofluoric. This is hydrochloric. Well, the difference here is that if it ends in ate, we just don't put hydro in front of it. We just call it nitric acid. That's all. So HNO3 becomes nitric acid. Not hydronitric acid, just nitric acid. So if you ever hear the word hydro in front of an acid, it's a clue that it's going to involve a binary one, which is just a hydrogen with a single element. If you have a hydrogen with a polyatomic group, you'll never have the word hydro in front of it. You'll just change it to the 8, becoming ic. And I have a really simple, silly way of memorizing that. It's dumb, but it might help. Sometimes you ate something, icky. I ate something, icky. It's dumb, but maybe it'll help remember it. Well, the same logic, though, works if you have a hydrogen with a per8. ClO4 is perchlorate. Well, that just makes this perchloric acid. Right. All you do is you just put the per in front. It's one of the reasons why we can't have the hydro in front. Because right here we can't put hydro in front because, well, what if it was a per-ate compound? Well, then it becomes a per-ic acid. Okay, let's try a few more. Let's say we have HClO2. ClO2 is known as chlorite. So the naming scheme here is that anything that ends in ite changes to OUS. OUS. I have a silly way of remembering this. Let's say that you have an ite, but this is actually short for fight. You get into a fight, and someone gets hit. Well, maybe they would get hit in the stomach, and they might go, ugh! And so getting into a fight makes you go, ugh! Because you got hit really hard. It's dumb. Whatever. It's been an hour for this lesson. We gotta finish here. So here's how that works. If you have a hydrogen with something ite, you make it us acid. So because the thing in the middle is chlorine, it's chlorous acid. And finally, the last little bit here, let's say that you have a hypoite. Well, then it becomes a hypoacid. So if you have H, which makes it the acid, with ClO, it becomes hydrogen hypochlorite. The hypo gets kept, the ite gets changed to us, and it becomes hypochlorous acid. Wow, we learned a lot today. Okay. I got a few examples, but I'm not even going to talk about them. You can just look at this example slide here. Here's the thing I need you guys to know. I do not believe that this is the most effective way of learning how to name stuff. You don't just watch a 1-hour lesson and go, I got it. Okay, maybe a few of you actually do. That's okay, though. Everyone is a unique learner. Everyone learns at a different rate. We're going to spend a few days now, 2 or 3 days. We're going to work on this. We're going to practice this. We're going to do some activities. We're going to do some labs. We're going to do some worksheets. And we're going to practice getting better at how to name these things, because ultimately this is the basis of how chemistry works, is that you need to be able to name what you're talking about. So topic 5 is going to be for a much future day. We need to do some practice. Let's do a quick recap of what we learned about, and then we'll call her a day, and I'll stop the YouTube video. So I'm going to go back here to our original slide. Ideally, back in grade 9, you learned already some of this stuff. Hopefully this wasn't brand new. If it was, this was probably overwhelming. And to be honest, I totally understand if it was overwhelming. It's fine. I taught it all in a one big swoop so that we can spend some time practicing it the next few days. But ideally, you've learned how to name your covalent and binary compounds already. Well, then, today we learned about how to do the multivalent things that have a Roman numeral, and we learned how to do the polyatomic things, which have these like groupings that come as a unit. The final thing that I really should have mentioned is that there's also like a third category now of things that are acids. And acids have their own specific naming rules, and there are the 5 of them. So that's it. That's basically what we've learned today. We now need to practice learning how to really do both things. If I go back to a slide like this one right here, if I give you the formula, can you name it? Or if I give you the name, can you write the formula? So we'll spend a few days working on this. So if after this lesson you are feeling overwhelmed, it's okay. I kind of expect you to be, because this is the lesson that all of a sudden makes chemistry hard. It's also probably the first lesson that's new, because there's a very good chance that lessons 1, 2, and 3 might have all been review for you from grade 9. So this is really the first new information, perhaps. So, like I said, we're going to spend some time working on this. So let's end our lesson. It's been 1 hour and 3 minutes. Hopefully you've more or less finished this in class, or somewhat close to, a little bit of on your own time. Let's call it quits. Like I said, though, please make sure you ask me questions. Please put up your hand and get some help. Come during Flex. Please, in Moodle, write your reflection and write some thoughts about what's new, what you've learned, what you think you need to work on. Don't forget to do that reflection at some point. 5 minutes, please. So, okay, let's talk later. Thanks everybody for watching the video. We will see you soon.